Good afternoon, everyone. So today's we be going through the week 10 of the deep learning material, and I hope you have went through the this week material. So this week is kind of a related to image processing, where we'll be talking about how to classify images, image segmentation, and all. And like the last week, we'll be solving again. We'll be first of all going through the concepts which was covered during this week, and then we'll be solving the assignment 10 of the last year so that it will be easier for you to do the assignment. Okay. And if you have any question in between, do let me know. Okay. So let's see what all was covered during this week. Okay. So basically, we'll be talking about convolutional neural network. So as of now, we have seen the feed-forward neural network, okay? And we were just talking about feed-forward neural network and how to train a bigger networks. We talked about, okay, some of the training strategies and all, okay? And last week we covered related to NLP thing that if we have given a certain set of weights, a certain set of words, how to convert into a vector form, okay? And previous that we covered about training strategies, bias where instead of we talked about autoencoders, the construction of the images, then eigenvector, eigenvalue decomposition, PCA to visualize the high dimensional data. Then we talked about the optimizations techniques, which is covered. And prior to that, we were talking about the pitfall and rain and fall. So this week and in the upcoming week, we be just going kind of a new kind of architectures, which is, for example, the CNN. CNN is very much useful in the image processing, okay, in the computer vision community. So these are just some of the techniques which varies from field to field, okay. So every field, for example, NLP community have a transformer, computer vision community have a convolution, okay. So every community has a different kind of architectures. So, and it is based on the data type, basically. Okay. Every data type is of a different format, different structure, different relation and all. So it's very much necessary to have a different technique as well. Okay. So next week we'll be seeing RNN kind of architectures, which was very much common in the last decade, but after 2018, the transformer took it over. Okay. And lastly, the last week, it will be completely based on the attention mechanism. Okay. That will be quite new in the field, basically. From 2018 onward, we just have autoencoder means attention mechanism, self-attention, cross-attention, and it's all over NLP and image processing community. Okay. So the thing which was covered in this week was the convolution. Convolution operation. And then it was covered about if we perform on a 2D image, how we perform CNN, means convolution neural network, how we perform. It will be talking about filters, height, weight, and the size, how to classify it. Okay. Then it's mainly just about techniques, which, for example, the max pooling, mean pooling, weight sharing, and all that, and different kind of architectures like LXNet, BGG, ResNet, Inception Net. These are kind of a different techniques, which different architectures by the different research groups. Okay. And finally, some of the techniques to visualize the filters and all. So I don't think we'll be covering the visualization of filter of CNNs and all. Maybe just look into the concepts which is necessary for solving the assignment problems. Okay. And if we haven't went through the lecture material for the this week, I hope you go back and see, because I was going through the PPTs and literally the content is too nice. Okay. And a lot of intuition explanation has been given about CNNs. So I may not be covering in that much depth because I assume that you already know certain stuffs. Okay. But yeah, it's always good to know, learn from a different people's. Okay. Some people give you more, what I say, intuition about certain things, what they have. So it depends upon person to person. There is nothing harmful in learning from different person, different techniques and all. Okay. So let's see about the week one material. Basically, that first of all we'll be discussing, and lastly we'll be solving assignment problems week 10. Okay. So it's the assignment problems. It's so much based on the techniques on the CNN only. Okay. So let's start with. Okay. Okay. So I will be giving you one intuitive explanation of what is the convolution operation is all about. Okay. And it's just not about 2D images or anything. It is applicable everywhere. Okay. Because in the end, we are dealing with the signals. In 2D images, you can see it as a 2D signal. In NLP, the words you can see as a 1D signal. Okay. For example, in words, for example, each word we have a vector. Then after each and vector, if we just plot with the time, it will be making some sequence. Okay. So this is for the NLP thing. Okay. In the image, this is how the data is given in NLP thing. Okay. So basically, we are given n vector. Okay. With the time as a dimension, you can assume it as a 1D signals thing. Okay. Basically. So in NLP, you can interpret as a 1D signal. There will be certain spikes and trend of it 1D signal basically. Okay. Images, you can see it as in the NLP, we are having each and every tokens because one word will be coming after the second word and third word. And each word is having a certain vector form. Okay. And so you can interpret as I mentioned, as a signal, 1D signal. But in the images, we don't have a time as a dimension. We just have a spatial dimension. So you can interpret as a, whenever you see an image, anything, image, okay, it's kind of a 2D thing. Means we are having a 2D heat map, something, certain certain heat maps. So somewhere the color is very drastically changes. So that is how its images you can interpret as a 2D signal. Okay. So any data, any kind of a data can be interpreted as a signal. And that's the whole thing, basically. Whatever the different techniques people are coming, it is very much deep rooted in the signal processing community itself. Okay. Now, as I was suggesting about the convolution operation. Okay. So it's like we have been given, for example, let's take a 1D signal. Okay. So we have been given a 1D signal and we want to, for example, this 1D signal you can interpret as image. I mean, simple thing is we are on the bike, we are riding. Okay, so we are at particular position, we are having a particular speed, and then we are changing it with the time. Okay, yeah, it was V0, V1, so like that. We have been given a particular speed and thing. Okay, now the thing is what? will be the next time the speed will be. So we want to say something about it. Okay. It's kind of a very hard problem. Okay. Because if my current speed is 50 kilometer per second, and if I ask you what will be my speed at after 2 seconds, it's because something means and within 1 second the brake might be applied or something will be happening. But the thing is, there won't be a very drastic change. Whenever you apply a brake, it takes time. So the degrade means the deacceleration will be taking a time there. And whenever you are accelerating, it will be not like after 50 you're directly going to 1000. There is not that random change which is happening. So you can still say something about it. If I am at a 50 kilometer per second at a particular time, then the next time it will be most probably plus 5, minus 5. You can tell something that it will be within this interval. Okay. And yeah, that's the whole thing. Probabilistically, we want to quantify that what's the interval and thing where we might be falling. Okay. But it might not be the accurate. Okay. So the thing is, how can we be more confident? We want to make a prediction for the next time step, but can we say something just on the previous time step? No, it will be better if we use more information. So if I am at particular position Vn, I want to make a prediction at Vn plus 1, what's the velocity will be. Okay. And this n is a discrete time. Okay. So the question we are asking is that what will be Vn plus 1? Okay. Given that we know Vn. Okay. So this is the question which is initially we are asking. But we also have information Vn minus 1, Vn minus 2, Vn minus. We are also having a position that how the previous trend of a signal. So the previous trend, we are having actually the information. This problem can be more properly formulated as Vn plus 1 given the set of Vi such that I belongs from 0 to n. Okay. So we have been given this information from V0, and then we can, because we know the particular trend of how the trend of this signal is changing, and it will be capturing much more information as compared to just predicting based on the previous time step. Sometimes it's necessary to make a prediction just on the previous time step. That is the Markov assumption we are having. But sometimes we want to have based on the whole history. Okay, whole history, it might be, or the partial history. For example, the last 5 time step. We want to make to say something about it. Okay. So this whole thing can be more formally interpreted as uh, kind of a dynamical systems point of view. So what I mean by a dynamical system point of view, we can model the rate of change of the velocity with respect to time with certain function which depends on the current velocity. We can model this in this way. Okay. What we are saying that the rate of change of the velocity is a function at v and plus 1 is the function of the velocity vn. We can have a vn minus 1, vn minus 2 till v naught. Okay. So if we can model something like this, it's much more means interpretable. We just need to design this function f, that how it is changing. And this function f, if we can integrate it, okay, it will be giving us much more better. Means it's kind of an ODE which will be evolving. So the solution, if we want, for example, we are having, suppose if I give you dx by dt is just x squared. Okay. You know that how to take a derivative for, I mean, how to solve this problem. It's very much easy. Just need to take this, integrate both sides from 0. For example, initial position was x naught, and we want to know at position at x from 0 to t. So this kind of a differential equation we can get. Okay. And it's a unique solution. Okay. For this particular kind of an ODE. So it's always good to interpret the problem as certain kind of, I mean, certain modeling or certain assumptions should be needed. Okay, in any kind of a problem. It's not like that whenever you are given a problem, you just directly jump off to this conclusion. You need to model in certain way. Okay. So, for example, as I mentioned, in the feed-forward neural network, we are just trying to model the underlying function. Okay. We are just saying that we are given a set of input-output. We want to model a function which take this input and predict y as an output. Okay. So the same thing applies here as well. Okay. In the, for example, in LSTM or for example, in NLP thing. Okay. So what we are asking is that given a sentence is there, my name is, okay, or means the capital of India is there, and I want to know what's the next word. Okay, the next word we have definitive what it is. But the thing is, my sorry, capital of India is something. Okay, this is something we need to predict. That's the task. Okay. Now, each this of this word, last time we have seen, we can interpret this as r to the power n, certain vector form. Okay. So what it is happening in n dimension, we are asking that if I am at particular this point, I know I had this, I went I jumped at another point. So this is kind of a trajectory which it will be making. I want to know now at other point what is the most probably likely r to the power n, and that I can decode and get the answer for this. Okay, so this is kind of a modeling. We are trying to model this 1D signal, and we know the value of a 1D signal at particular instance, and we want to utilize the information of the whole past here. We are utilizing it. In NLP community, it's very much necessary to utilize the based all the past information, and that what leads to the transformers basically, which we'll be covering in the week 12. Okay. But I'm trying to give an intuition that what is happening, what we are trying to model. Okay. So the convolution operation, as I mentioned, we have been given, we want to predict Vn plus one uh, based on the past observations. Okay. So the thing is, if I want to make a prediction at Vn plus one, suppose I want to predict based on the past 5 observations I had. Okay. So I can write it from 0 to 5. Actually, it's 6 in this case in the programming language, but 0 to 5 means 0 to 4. Okay. Now I will be giving a weight based on the future, on the past. Suppose I want to have Vn minus I, where I ranges from 0 to 5. Okay. I am multiplying with Vn minus I as well. V of I. V of I. So this is a more proper format, what I'm writing. Okay. So I am trying to predict V n plus one, something, certain observations. Okay. Based on the past 5 observation, and each I'm giving certain weight. That's kind of a good thing, means good as well as bad. Both things are involved here. Okay. Good in the sense we are trying to use maximum information, because as we know, as I mentioned, if I at particular time instant, the vehicle speed was 50 kilometers per second. If previously it was around 48, and previously it was around 47. Okay. If I give a weight for the past, suppose if I give more weight to the recent observations. Okay. So suppose I have a 5 observations, Vn, Vn minus 1, Vn minus 2, Vn minus 3, Vn minus 4. Based on the past 5, I want to make a prediction on Vn plus 1. Suppose I gave a more weight. to this Vn. That is suppose for point 0.8. Point 0.8, no, let's miss. Want to make something which is useful. Okay. So basically, suppose I gave more weight 0.6, 0.2, 0.1, 0.9 is there, 0.00, suppose 8, 0.002. This is zero point 0.3. If I add this two, it will be 0.08 and 0.02. It will be 0.02, 0.08. So like if you see this function, I'm trying to give a more weight to my just recent one. And this is the weight as we are moving in the past. And that's how I'm just multiplying with the weight and trying to predict the next thing. Okay. So this is how I am trying to make a future prediction just based using the past information. And this is kind of a, you can think it of as prior information that which observation do you think will influence the mood? Okay. And it depends. It totally depends that here I am taking because I want to make a prediction on the future velocity given the past velocities. Okay. But the thing is, I want to because if I am at particular 1 hour, I am riding. Then from in 60 seconds, okay, suppose I know my velocity at 55 seconds. I want to know at 60 seconds what is my velocity, and I know the velocity at 50 and 45. What I know is that this recent velocity plays a very important role to predict it at what it will be at 60th. Okay. And this 15, it also plays an important role, but the correlation between 50 and 60, because we can have a large drastic change between 50 to 60. Okay. And the same here, it will be much more less, the correlation between 45 to 60. That's why I have given the low weights to the very past in the time and the more weights to the recent observations. Okay. And this is what the conversation is all about, actually. Okay. And it mainly depends on designing this weight factors. This weights means this is called as the weights filters, a lot of different weights, kernels. Okay. So I can call it as a weights filters kernel. Okay. So different area, this is called as a different area. Okay. And this is actually means so it's all depend upon using the past informations, assigning certain weights to them, and trying to make a prediction for the future. And to some extent, this kind of a modeling is good on only because we don't have any more information. So the problem is like that we have been given a bunch of past observation. We want to make a future observations. Okay. But the thing is, and also for example, just leave this thing. Okay. Now in the experiment, okay, as you know that whenever you carry out the experiment, you never get exact results. Okay. So, but we want to know that what's the exact true value. Okay, there is always a measurement noise and all. So what we do with the simple technique is that we will be taking an n observations. Okay. And taking an average across the n observation. That is what we used to do in, for example, in 12th standard. Okay. So in the physics practical, as far as I know, I did okay. So we were using there was a tool which measured the thickness, I guess. Okay, I'm not remembering it, the name of the tool thickness. Okay. So we were taking of 3 to 4 observations. Okay. And after taking a 3 to 4 observation, we were taking an average and reporting that as a result, mean and a standard deviation. So the more number of observation you take, the better the estimate gets, the better you know about the true value, because it's all due to by the law of large numbers. Okay, so if we have given a random variable x1, x2, till xn, which are IIDs from certain distribution D. Then x1 plus x2 till xn divided by n converges to the mean of the distribution. So this is what it states basically. So what are random variables and all? I'm not going to explain basically because I hope that you already be familiar with what are the random variables, what is distribution, what is IID means and all. And this is just summation divided. It's just an average in probability. It just converges to the mean as ends limit n tends to zero or infinity. Okay. So it gets better and better. We move towards the mean actually. So this is one of the interpretation for the convolution operation. Okay. One more thing I can give you is suppose I have given you a signal. Okay. And suppose it's of the length 1, 2, 3, 4, 5, 6, 7, 7 and this level. Okay. So images is always of the fixed shape, what is coming. Okay. Suppose the signal is of fixed length. It will make our analysis much more easier. Okay. Now the question is I'm asking is that I want to classify this signal basically. Okay. And I know that there is means this is a one day signal. And suppose we have a time dependencies. It's a time versus certain signal. Okay. But I want to classify this signal. That's the problem statement. Whether this signal is of a human signal means human we have, for example, I'm speaking, I have a certain frequencies, and animals speak, they also have a certain frequencies and all. Okay. So I want to ask the question that basically that classify that whether it's of human or not human. Suppose this is the tough. Okay. But the thing is, I am just given a different samples, and each sample I'm just given certain length I'm given, and I'm just asked to classify it. The question it seems easier, but the it's not as easy as it seems. I'm okay because I can't take what operation should I do? Okay. So mainly what you'll be thinking is that taking a feed for a network classify as 0 and 1. That's kind of a brute force method. Okay. Brute force in the sense actually here we know that on the next time step, it's dependent on the previous time step as well. That's the bias, which I already know. I want to incorporate that into my model. Okay. The next time step is dependent upon the previous time step. This assumption does not hold for the feed-forward neural network. There we what we know is that at each and every instant, whatever data point is seven, the features, they are IIDs. That's what the assumption we make in the feed-forward neural network actually. Okay. That is needed, for example, if you want to classify in the bank, okay, a person, its salary, you are given it, you want to classify defaulter and faulter, something like that, and you'll be given a person, his salary, his job, okay, this sort of thing. So there we make an assumption that a person and his salaries are independent, these two features, the person male or female, and his salaries, whatever. But whenever you assume that there is a relation between a man and his salary, woman and his salary, then the feed-forward neural network does not hold. Okay, different data have a different bias which need to be hold. Okay, and that is what about this neural network at all. Okay, people are coming with the new and new architectures, new and new biases for the different data types. Okay, one bias helps for the particular data set, but it does not work for a different data set at all. So the one simple brute force you can try is that on the image classification, just take a MNIST data set or MNIST no, C for 10 data set, okay, and just make a big vector out of it, try to train a very big neural network using in the PyTorch, and just try to see how it perform the test data. It will perform too poor on that. Okay. So that's the thing. You know that in the images there are certain correlation I will be talking about. Okay. So what we are doing in the convolution operation is that we are using a weight. Okay, this width suppose I am keeping as a 3 because it should always be lesser than the 3 and maximum length can be equal to the length of the signal. Okay. I will be just placing it over on the signal and moving one at a time, and I'm getting a feature. So you can think this filter as a basis. Okay, what are the bases? In the Euclidean space, we talk about x-axis, y-axis, z-axis. That are the bases. I'm given a point 1, comma 3, comma 3. On that 1, comma 3, comma 3, 1 denotes the x-axis, 3 denotes the y-axis, 3 denotes the z-axis. Then I can localize on these 3 axes. Okay. The same thing applies here. But here, our basis, one basis is it's a vector form. Okay. I'm again repeating. This is my basis. After convolving it, I will be getting a signal of different dimension. Okay. I can pad it in front. So this is a coefficient. You can think it of as a coefficient. And this is my base. This is my as a base or yeah, basis. Okay. So I am taking an input signal. I'm trying to project using the basis. I'm getting a coefficient. And using a coefficient, I'm trying to classify my signal. Okay. And this is what a convolution operation. This is one of the thing. The more number of bases you are taking, the more number of you are trying to define it because as a signal, ideally a signal lies in an infinite dimensional space. Okay. Because the signal is always a continuous entity, but we have been given a certain in between discretized version. Okay. So the more number of bases you take, the more the better approximation and the more better coefficient and the more better the model will perform actually. Okay. So this is what one way of looking into the convolution operation, and I found it much more intuitive. This is the basis. We are trying to take a signal. Whatever the signal is coming, this basis, we make it enable in the network. Okay. And we'll be getting a feature as certain output. And using that feature, we want to classify our signal as something human, non-human, something like that. So this is also one of the ways you can look the convolution operation as well. Okay. So I hope I have given the two things about the conversation and will be clear. Okay. So if you have any doubt, do let me know. So conversation operation is just basically about there can't be a drastic change at particular position because the nearby. So it's like for example, uh, I'm given a data set which is something like this. This is x-axis and y-axis, and this is of certain one class. Then this reason you already know it will be also of the same type because if it is a very small thing, because there can't be a drastic change and it will be of different class. Okay, so this is the normal thing which we are trying to model it as. If I know a nearby pixels, okay, the center pixel value should not drastically change. If it is changing a drastically something, then there's something wrong actually. Okay, because for example, you are seeing any image you take of a dog or something, anything, okay, any wall, okay, and you know that my wall is of pinkish color, okay, at particular pixel, it will be, or if it's nearby pixels are pinkish, the center pixel should also be a pinkish. It can't drastically change. The changes is always of certain smoothness. Okay, it happens only when, for example, I have a background. This is and there is certain object is there. So at this region, there is a drastic change, and which shows us that there is some certain object. Whenever there is a drastic change from pinkish, it's going to reddish or something. There is certain object which is there. Okay, but if my nearby all the pixels are pinkish, then this center pixel should always be a pinkish. Okay, so that is how you can detect a edge. You can detect a random change, and whenever there is a random change, it emphasizes that there is certain object which is present. Okay. Okay. So in the image, if you see, images are stored in the form of pixels. And the more the HD pixel, for example, you might have heard of high definition videos, images. So the more number of pixels you store, okay, and it can go up to infinity actually. Actually, the image you are seeing, it's a continuous signal. And that continuous signal, because we want to store in our device, we take and discretize it and store its value over the region. Okay. So 64 cross 64 pixel, if you take a 128 cross 128, 128 cross 128 will be having a more information as compared to 64 cross 64. Okay. So it's kind of a, because it always is good the more number of pixels you are having, because the more better you can understand that means the underlying signal or underlying images. Okay. So this is uncertain how this one square denotes one pixel. Okay. And each pixel is having a three channels RGB. These are the primary colors. And the thing is, so it's kind of a 3D array. So you know about a scalar quantity, we know about vector. If you extend vector, you'll be getting a matrix. If you extend a matrix, you'll be getting a matrix concatenated along with the matrix. Okay. So like that, it can go to many dimensions. So it's of a 3D. Okay. And each pixel value lies between 0 to 255. That's the normal thing. This integer value. Okay. So for example, this pixel, if you see, as I mentioned, there's a correlation between this pixel and its nearby pixel. Okay. It is correlated with the nearby pixel. There can't be a random change in a pixel. Okay. There are few instances it can be. Okay. Because most of the images we see, it's kind of very much discontinuous. Okay. So discontinuity in the sense, my signal, for example, certain types, and there is certain spike here. This is called means very random change. So this kind of an signal is not good, because here, if you know, I would have interpreted like this. Okay. But whenever there is a spike, it shows that certain object is there, or certain very much, if something is very different is happening though, actually. Okay. It might be due to a lot of reasons are there actually. So for example, you might have heard of the news that scientists have discovered the new planets. Okay, but the original thing is that they tag the waves, and whenever there is a random change in the waves spikes, it ensures that either that is might be due to a planet, star, or something, and that is how they study more and study about a trajectory. That is related with the signal processing thing. Okay. So we know that if my wall is there, okay, if my nearby pixels are pinkish, then it will be a pinkish in the center as well. Okay. So that's the one thing. There is a correlation with the nearby pixels. That's one thing. Now the second thing, let us consider. I have a dog here, means human suppose here. I have a human here. Okay. So one bias we know is that in the images there is a spatial correlation. Okay. And one more thing is that with the help of a filter, I can track a random changes. So for example, there was a few filters which were shown in the this week lecture. So it was all ones, for suppose. Okay. It will just blur the image. If you just take something like this, 8 minus 1, overall the value is 0. But this kind of an edge detector, okay? So the thing is, if I place my filter over here, this man, and if I place my filter over here, so the thing is, I want to means I would have taken a different filter as well for the different position, okay? But that is not good actually. Why it's not good? Because if my man is present here and man is present on the top as well as down, okay? I want to convey the same meaning to my model. I want to say that here it's also a man I have detected. And whenever the filter goes here, it should also tell because my input signal is the same. This too, the next feature we be getting, it should be the same actually. It can't be where I am getting a different feature for this man face and the same man is on the down. It will be a different feature. That I don't want. Okay. So that is why we converge the feature. We take a 2D image, we take a filter, and we just slide it. We just move the fix across all the over the image basically and get a feature. And it ensures that if my certain feature is present across any on the top, down, bottom, up, everywhere in the image, it can always detect the position irrespective where it is present. That is, it is translation invariant. Okay. So translation invariant means if my object gets changed, my feature won't change. It will be detecting the same feature. Okay. So that is kind of a thing we wanted actually. Okay. So this was about this thing. And so in the images we have in the form of pixels, I'm taking a 2 cross 2 filter. I will be placing it over, getting certain features, just a summation. And you can think of as a non-linear kernel as well. Okay, if someone wants to do a research, they want because we are doing a linear combination W1 time X summation over all the pixels. That's what we are doing actually. Okay, but you can have W1 time X square, something like that. You can also do. That is one of the direction you can look into. Okay. I am not sure if people have tried, but the one thing is that we can just take and have a polynomial feature on the top of that. Okay. So now again take this kernel, move it, get a feature. Again take it, get a kernel, get a feature. So in this case, we took a 3 cross 3, we got a 4 cross 4 as output. And this kernel. So you can think it of as this kernel as a basis using which we decomposed our signal and we got a much more lesser size coefficient. And using that coefficient, we will be classifying our image. So that is one of the intuition you can have to understand the convolution operation. So there's a lot of different convolution operation with kernel. Okay. So previously, before the last decade, people were trying to use what I say. They were creating a manually this filters and all. That was a whole research thing before 2010. But the thing is, when this we got into the CNNs, okay, and the GPUs came into the market, we had a frameworks to train our model, neural network, whatever you're saying. This means it's kind of everything is gone actually. You can't imagine that in the 2000 people were manually creating the PhD thesis were dependent upon that actually. But with just one drastic change, everything changed. Okay. This kernel, we were able to learn from the data itself. Okay. And everything got changed actually. Everything. We don't need to manually create a different kind of filters and all. Okay. So that's how the research progress actually. With time, you might be thinking that what that person might have done. Okay. But actually, at that particular instance of time, that was necessary. Okay, every research, whatever you are doing here, after certain time, it might be feel like that it's useless. Okay, but that was actually the necessary. Whatever every, it's kind of an incremental. The next thing is built on the top of the previous things. Okay, so That's how the deep learning is drastically changing every day. You don't know, okay? Transformer, it came into 2018, okay, and everything got shifted into the transformer now. So there will be always be a sudden change, drastic change, which happens in the research community, okay. And but that does not mean that LSTM or any kind of architecture is born. They're still means used, okay. So, but I guess by looking into the slides, it's pretty much everything was covered actually, okay. And literally, the CNN thing, it's better if you see the images, how they are convolving it. I can't show here on the my iPad, okay. But the PPT, I will be just saying that just go through the material actually again, okay. You will be properly understanding what is the CNN, how it operates. And whenever you are writing a code, it will be helpful for you. Okay. So let's see one more thing which we need for the assignment basically. Okay. So the slide basically the one thing is if we are given an input image of the size W cross height cross number of channels is D dimensions. Okay. I, I am convolving it using a filter of size K cross D. Okay. I want to know what's the output shape. So there is a direct formula actually. So this D and D remains the same. Okay. So the height suppose is weight means height with is W dash H dash dot D dash. If we are using n number of kernels, D dash number of kernels, that will be D dash. But what's the H dash and W dash? So W dash, you can think it of as W because that is the original shape we are getting. But whenever you do a filtering, that number of pixels, the size it get is reduced. And again, you add a padding, you add on the top and down, and the stride. So it's a normal formula which makes intuitive means intuitive explanation whatever it should be. More intuitive explanation is given in the lecture, okay? And again, we might have added means got a lesser shape, so that's why it's +1. And sometimes it's taking a seeding value of this. Okay. And the same thing applies for the width as well, height and width as well. So how the normal CNN neural network, actually, what's the advantage? Basically, okay. Few of the advantage, let me tell you, okay. The CNNs. Using CNN, we are doing a weight sharing because we are taking a same weights again convolving over the images. So for example, for example, my initial image was a height cross width. So initially, you might we needed height cross width time this many times of weights using feed forward network. But whenever you are doing with the kernel K cross K, the only weights is K cross K, and this is very much lesser than height cross width. It is very much lesser. Okay, if my image was 1024 cross 1024, but whenever you're using kernel of 9 cross 9, it's much more lesser. Okay, so you can think it of as means computationally it's very much better. Okay. Okay. So that is weight sharing which is happening. Same weight we convolve it. Okay. And it is sparse. Okay. And the third thing is we know inductive bias. That is a special correlation. So that is kind of inductive bias we are having. Okay. So these are certain of the advantages, main advantage, and it generalizes better than normal feedforward network. So what do I mean by generalization? Okay. The thing is, whenever you're training a model on the training data set, it might be performing 99%, 90, 100% even. Okay. But that is not, you can't judge the model just based on its performance on the training. Okay. So, imagine, for example, Tesla car is that it has been trained on tons of data set, but it is not performing in the real-time data sets. Then it's totally useless. Okay, so that's why we have a training and the testing. We want a model to perform better on testing without being trained on them. That's how we judge the model performance. Okay, and that is why we call it as a generalization. Okay, in the deep learning. So let's now see about how the normal architecture of CNN looks like. Okay. So maximum of the architecture, they are just inspired by, means they have a certain intuition. Okay. Why you need to have your architecture in certain ways. There's no intuitive explanation for that. Computationally, it works. So whenever you need to construct a convolution operation, try to see how the people have created in the resonant block, because that's the something computationally people have tried and it worked out. There's no intuitive explanation that you should have architecture in this way itself. You need to use max pooling, mean pooling, average pooling. You just need to check which one works best for your case. That's it. Okay. So there's something about one thing about this architecture is that, yeah, you have an explanation why you need to use CNN, but in CNN, how many layers you need to use, how to construct this pooling explains. There's a no intuitive explanation. That's just the experimental part. Okay. So that's how the people have tried 1,000 of architectures, and now we know that some of them works. Okay. So you might be you can go and just construct a new kind of a CNN architecture without seeing the architecture the people have already used. Okay. Just construct a different 9 cross 9 kernel size, anything. People, okay. It won't work out actually, because 3 cross 3 people have found odd number of kernels, they work better than even number of kernels, even size kernels and all. So initially you'll be having an input tensor. Okay, we'll be performing a convolution on the top of that. So this is kind of a convolution. We had a basis, we got a set of coefficients for that. Okay. Okay. Then the thing is, again, you can go on the convolution, but as we have seen, we need to add a non-linearity. So instead of the non-linearity between the convolution layers, usually the thing people have to, means this is all the heuristics actually. Okay, there is a no intuitive explanation, just on the experimental as I mentioned. There is a pooling, you just take again a kernel where you take a maximum value of it and again get the same reduced dimension basically. Okay. Again, you do a convolution on top of it. So this pooling, you can think it of as adding a non-linearity. Okay, it's a non-linear operation. Okay, and again you just construct convolution, again pooling like this. You can have a many layers, and finally until unless you be are just restricted with the 1 cross 1 or something. Okay, either you can flatten whatever you are getting, and on top of that you can have a feed forward network, and the output is number of classes you are having for the classification task. Okay, so this is how the normal architecture looks like for the CNNs. So I guess that's what all is needed actually. Now you know about the convolution and all. So the different architectures, they have just a different thing. Okay, I'm not going to talk about the architectures and all. So if you want to know more, just go to the lecture material. So it has been very much intuitive. You can just see what kind of operation people are performing in different architectures. But one thing I'm just talk about is the ResNet thing. What's so special about this ResNet? Actually, the ResNet is the real time. You can see it is finding a equilibrium point. What do I mean by equilibrium point and all? That means really. So we have an input as x. Okay. Now we perform certain operation on top of it using f. We be getting f of x. This f you can think of as a convolution. Okay. But the thing is, as you increase the number of this convolution layer, there is always one of the problem which happens in any architecture if you increase the number of layers, which is vanishing gradient. Vanishing gradient, this is one, or exploding gradient. So majorly this vanishing gradients, for the exploding gradient, we have a solutions which works out to some extent. Okay, but the vanishing gradient, we don't have a much solutions actually. Okay. So this vanishing gradient by the name itself, the gradient we take with certain of the loss with certain weights, it is approximately equal to zero whenever the weights we are taking from the in the backward layers, basically in the initial layers. Because you calculate a loss, you back propagate the loss, and whenever it reaches in the initial first years like that, at that time it's zero. So the weight does not get updated at all. Okay, so that's the vanishing gradient problem which happens, and the performance doesn't improve after some time. So you're not able to train properly the model. So in the ResNet, they did one choice. They added it as here. So basically, you can think of this whole operation that is h of x is basically h of x plus x. Okay. So the thing is, you are just adding input again to my after performing the operation. You can think it of as at I am at a particular dimension, and this f of x is kind of modeling the derivative. Okay, so I'm adding a derivative, I'm moving it. And if you do it again and again, I'm creating a trajectory in the feature space. Okay, and it's a ODE, it's a differential equation. It's a discrete time differential equation. Okay, and if you do this for infinite number of time, you'll be finding a point x star such that after performing this f of x plus x, it will remain constant. That is, it will reach a particular point where my input feature, this feature refinement won't happen. Okay, so that's the different thing I talked about. Okay, and they observed that using the this skip connection and all, my model was able to perform better, and I was able to increase 150 layers, 200 layers, even 1000 layers you can go up to. Okay, so that was the main thing which people tried. It was just also a heuristic when they tried it. But later the mathematical concept developed on the top of that, that what's actually is happening. Okay. And also this week they talked about, I guess, guided backpropagation optimization over images, create image over from embeddings. That is for just for you to know actually. Okay. There is no means it's just what happening in the community in the computer vision. Okay. And different application. Okay. So let's move to solve some problems from the B10 last year. So the first question is, which of the following think or three kernel work for the edge detection task? I have covered as well as in the weak material. For the edge detector task, the center pixel value should be negative and the surrounding should be positive. Okay. And it should sum to zeros. Okay. So the answer is basically 1, 1, 1, 1 minus 8, 1, 1, 1, 1. Okay, so this is the answer. The second thing. Second question. Suppose we are given a 9 cross 9 image I. Image dimension is 9 cross 9. And we apply a convolution kernel C of size K 4 cross 4. What is the size of the resultant image R? And the padding, you can assume it to be 0, and the stride is of 1. So the formula we had was 9, as padding is 0. Filter size is 4. Padding is 2, comma 0 divided by 1 plus the resultant shape R. If you do this, 9 minus 4, that is 5. 5 plus 1, that is 6. So the answer is 6, comma 6. 6 cross 6. The third question. Okay. Third question is related to an architecture. Okay. And it's related to architecture. Okay. Let's see. I am just gonna draw that architecture. This is the first thing. After that, we just got another tensor, another tensor, another tensor. And then we have flattened it. Sorry if my diagram is not that much intuitive. Okay. It is basically 8 cross 128 cross 128. After performing a convolution or a max put, we perform a max put here. Max put just reduces the size by half if it's even 8 at the rate 128 cross 128. Then we perform a convolution. The channel size got increased. It's sorry. It's, after convolution, my size got reduced to 64 cross 64. Okay. Now after convolution, it is 48 cross 48. Again, max put. The channel remains the same. 16 cross 16. And after flattening it, 16 cross 16, where D is the depth of the layer, H. Okay. I did a flattening, then it's converted into 1 cross 256, and again 1 cross 128. Okay. What's the dimension of the individual filter in the initial layer? Okay. So from 128 cross 128, we got into 64 cross 64. Okay. So question 3. Okay. 8 means at the rate before, that's the channel or dimension. Okay. S is the one, that is the stat is one for all the operations. What's the dimension of the individual filter in the initial layer? Okay. Since the stat is one, dimension of the filter, if we want to find out, it's from 128 plus 128, we are going to 64 cross 64. Okay. Why the depth is same? So suppose is the 128 cross 128. So after performing the kernel for the max pools, they have asked. Okay. So And we are going from 128 cos 128 to 64 cos 64. Okay. So the thing is, the stat is one, as the stat is one for us. Okay. And the input is 128 cos 128. Okay. And we are going, the final dimension is kind of a 64 and plus 1. It's kind of a reverse of the formula we were doing on the top. Okay. So we were doing the width is equal to width dash minus f plus 2p plus 1. Okay. So here it will be 65. So it will be 65 as the number of channel remains the same. That will be the same. So the answer is 64, 5 cross 65 cross 8. That's the first, third question. Fourth question, how many filters are there in the initial layer? The number of filters as there is remains the same after the max pooling. Okay. So it is 8. If the dimension of the filter at max pool 1, okay, there is 38 cross 38 cross 8. The number of filter is 128. Okay. What's the size of the dimension of the output layer? So 128 minus 33 plus 1. That's a simple thing. You just need to use W dash is equal to W minus F plus 2P divided by S plus 1. And the stat is 1, so it is removed, padding is not there. So W minus F plus 1. Okay. That's the normal thing. Now the sixth question. If this done. Sixth question. What's the new innovation in Google Net? Use of one cross one conversation. Yeah. They have used one cross one conversation in the Inception Net, Google Net or Inception Net. Use of different multiple sized kernel in a single LS. They have used 1 cross 1, 3 cross 3, 5 cross 5, 7 cross 7, or 9 cross 9. Till that they went. Average pooling. Yeah, instead of max pooling was famous at that time, but they used the average pooling. So the answer is BCD. And again, it's just a, a heuristic intuitive. There's no explanation for it actually. So just a person want to get 1 cross 1, 3 cross 3, 5 cross 5, 9 cross 9, 13 cross 13. It just depends. Okay. We have a two image, following two image. We observe the neuron is in third layer of the CNN. Which of the following statement is always true? Okay, so the image is given and initially the open is written. And again, we have passing the image like this. Okay, now they have asked us that we observed that a neuron is in third layer of the CNN. Which of the following statement is always true? The neuron will fire again because both images contain the word open. The neuron will not fire again because the word open is open is different. It's written differently actually. Two things, okay. And here the image is kind of a dark and blurrish, and here it is not. So the correct answer is that no, it does not understand. It's just a filter. It just can detect the edges, but whenever you change the orientation of word again and again scattered, it won't. The answer is none of this. We have taken a CNN to detect dog faces. We find that CNN is good in detecting dog images taken in a park, while it performs poor on the dog images taken in a house. Yeah, that's what I was talking about. We have an image. If a background change, our model perform poor, but it does not understand actually. We just say that the filter it will do the work and all, but no, it doesn't actually. Okay, it just work on the same kind of a distribution. Whenever the distribution changes, distribution in the sense, if you train a model on a very few men and a large number of female, and if you again and no simple thing, we just train a model on the Asian dataset and try to see its performance on the American dataset. It will perform poor there. That's a distribution thing. Shit. We observed that occlusion experiment to inspect this phenomena. Which of the following observation we are most likely to observe? Occlusion of the eye of a dog causes the large drop in the probability of prediction. No. Occluding the tail of a dog causes the large drop in the probability of prediction. No. Occluding the nose and ear causes the large drop. No. Occluding the glass causes the large drop in probability of prediction. Yes, because initially the dog is present in both the normal park images and the house images. But the thing is, where to focus our model doesn't know actually. It does know it will be focusing on the eye, tail, and all, but the glass it also focusing, and we see there is a large drop actually. So that's the reason for this. Question 9. We have trained a CNN. We have the picture on the left, which we feed into a network as an input, the label human with a high probability. The picture on the right is the same image with some added noise. If we feed, so basically we have one image, the normal noises image, and it predicted as a human. And again we corrupted some noise, which we talked about in the previous weeks, and we passed with our CNN model. Okay. Then they're asking what the model will predict. CNN will detect the image as human. CNN will detect not human image as a human since noise is added to an image. CNN will detect the image as human but with a lower probability than left image and insufficient information to say anything. So actually, this question doesn't make sense. Actually, adding a noise, it depends how much the model is trained. Actually, okay, we don't know how well the model is trained, what's the decision boundary, and whatever the function it has learned. We don't know anything. It might or might not detect as a human with certain high probability or low probability. Okay. So the correct answer is D, insufficient information to say anything. And lastly, which of the following architecture has the highest number of layers? AlexNet, GoogleNet, VGG, ResNet. Actually, the ResNet, it's having a large number of layers as compared to all the other architectures. Okay. So I hope you enjoyed today's session. Okay. So if you have any more doubts, anything, feel free to ask.